Good morning class and welcome to another lecture in sustainable energy technology. In the previous class we started our discussion on wind energy and today we will continue that discussion forward. One of the most important things to realize when we are designing a wind energy power plant, a wind turbine farm say, is that wind energy is extremely variable from location to location and is also extremely variable between different times of the year and even different hours of a given day in a given location. This is very relevant in order to understand how much power can we expect out of a wind turbine from one day to another day, from 1 month to another one, or from 1 hour to another hour on a given day. So the understanding of the variability of a wind resource in a given location is extremely vital for a proper design and understanding of the expected power production that is going to happen from the proposed wind turbine power plant. So let us look at a specific probability distribution of wind resource, wind speed with respect to number of hours at a given location, say. So here what we are showing is a graph which gives you the probability on the y-axis and the wind speed in meters per second on the x-axis. The wind speed basically varies from 0 to 26 meters per second and it is kind of a discrete wind speed graphs. So 1 meter per second, 2 meter per second, 3 meter per second. So it's kind of a bar graph kind of a structure. And for each speed, there is a certain specific probability value that is attached to that speed. So for example, at the given location that we are studying here, the wind speed of 4 meters per second is likely to occur with a probability of 0.055. Okay. Now the total probability, all of these probabilities put together should come up as 1, because at a certain location there will be some finite wind speed at any given time. It can be 0, it can be some other non-zero value, but it must have a value. So the total probability must come up to 1 and the probabilities of the individual wind speeds are plotted with respect to the discretized wind speed values at intervals of 1 meter per second for that given location. This kind of a structure is called a wind speed distribution. So we see here from this specific location the values of wind speed for which we have the highest probability is around 9 meters per second or 8 meters per second, which is around 0.080. Okay. So what is typically done in these kinds of cases is that we have an anemometer which measures the wind speed at a certain location, at a certain height. The height will be the height at where the wind turbine is going to be placed. And we measure the wind speed over a period of time, say 1 year. Okay. And we measure the wind speed at certain time intervals. Say after every hour we measure the wind speed and see the average wind speed for that hour, etc. Okay. And that way, then we can club the wind speed values together into specific total time. That is, how much time over the entire year, say, wind speed of 8 meters per second was obtained, or how much time over an entire year is a wind speed of 10 meters per second obtained. So if the hour is, say, the unit of time, and in an year you have around 8,760 hours, 365 into 24, then this 8,760 hours can be separated out into the number of hours for which wind speed at a certain specific speed value was blowing. So say for 300 hours, wind speed at 4 meters per second was blowing. For 600 hours, wind speed at 5 meters per second was blowing, etc., etc. Then the probability of wind speed for that specific value, say 4 meters per second, it was 300 hours, then it's 300 by 8760 hours. That is the probability, 300 by 8760 for wind speed of 4 meters per second. So let us look, so that is just an example. So we will just look into the formal way in which we can use this idea and formalize it into a mathematical structure. So we will do that next. So we are doing wind speed analysis. Okay. So an anemometer measures wind speed throughout the year at different times of the day. Okay. The readings are classified within intervals bins of, say, delta u. So these are classified into velocity intervals. So in the actual graph that we showed, velocity intervals were 1 meter per second. We can also say velocity intervals of 2 meters per second, or and non-uniform velocity intervals can also be chosen. Okay. So this gives us, say, if you take a velocity interval of 2 meters per second, 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, and this goes on up to, say, 20 to 22 meter per second. So these are all individual bins in which we are distributing the velocities. All right, and we are saying, say, the minimum velocity is 0, of course, and the maximum velocity we are getting at that location is 22 meters per second, and so we are binning them into these kinds of velocity intervals. All right. So let these intervals be called I. So here I is going from interval 1, interval 2 up to, say, interval n. Okay. Where the velocity goes from ui minus 1 to ui, then the next interval is ui to ui plus 1, okay, etc. Okay. So for example, if you have the second velocity interval, then the second velocity interval corresponds to u1 to u2, then u2 to u3, etc. Where u1 will be the velocity 2, u2 is velocity 4, u2 is velocity 4 to ui plus 1, u3 is velocity 6. Okay. Then let the number of readings of wind velocity falling within a given interval the ni, then total number of readings is summation ni over all the I intervals. So then the normalized number of readings per speed range is given by Fi equals to Ni by delta Ui, where delta Ui is Ui minus Ui minus 1. Okay, and Ni is the number of readings in this interval, velocity interval Ui to Ui minus 1. Okay, so this is called, note here Ni is a number and delta Ui is a velocity. So unit of Fi is meter per second inverse. Okay, so this is the number of readings per meter per second. Okay, number of readings per unit velocity for ith interval. This is also called frequency distribution. Okay, so this is the frequency distribution of the ith interval. So we are doing this because in many cases the interval width may be different. So initially maybe you are doing 2 meters per second, then somewhere in between you are doing 1 meter per second, and then again you are doing say 3 meters per second. So if the delta Ui value is different for different intervals I, then this helps to normalize the number of readings per interval. Okay, then the probability distribution of wind speed is given by phi ui equals to Fi by n equals to Ni by delta Ui by n. Okay, this is the probability distribution of wind speed for the uith interval. Okay, again the unit here remember is meter per second inverse. Okay, so this is the PDF of the wind speed. Okay, for a discrete set of readings, this is gives you the PDF value, the frequency of the ith interval by the total number of readings over all the intervals. Remember n is summation ni. Okay, so here n is given by summation ni, all the number of readings put together. Then phi ui delta ui is the probability Note that phi ui is meter per second inverse, delta ui is meter per second. So this is a unitless variable as a probability is supposed to be. Probability that the wind speed is in the ith velocity interval given by ui minus 1 to ui. Okay. Then summation over all the intervals phi ui delta ui equals to 1 as you would expect. Okay. And you can see this from here also. Phi ui into delta ui is ni by n. So summation over all the ni's, this becomes n. So this becomes n by n. So this is equals to 1. So this definition is satisfied. The definition that the probability when you integrate over the entire range must be equal to 1. So now that we have defined the probability distribution, it's easy to understand what the mean wind speed will be. Okay, so the mean wind speed we'll call this u within square brackets, this kind of brackets, as summation over I phi ui into ui minus 1 plus ui by 2. So this is the average velocity within the distribution. That interval, ith interval, varies from ui minus 1 to ui. So the average speed within that interval is ui minus 1 plus ui by 2. We are multiplying this by phi ui, the probability distribution. And this divided by summation over I phi ui. Okay. So this is the mean wind speed as given by this system. Okay. So this equation will help you evaluate the mean wind speed for your distribution. Okay. Another important variable, and we will discuss why this is important, is the mean of the cube of wind speed. We will see why this is important. We already know a little bit of why the cube of wind speed will be important when we looked at the power. The wind power was proportional to the cube of the wind speed. Okay, so in order to find out the wind power distribution for a given wind speed distribution, we have to correlate it with the cube of the wind speed. Okay, so there this mean quantity becomes important. So this is u cube. So this is given by summation phi ui ui minus 1 plus ui by 2 whole cube by summation phi ui. Okay. So for a given wind speed distribution, the available power per unit area is given by Pu equals to half rho air into U cube. Okay. Then the probability distribution associated with wind power is given by P ui phi ui equals to half rho phi ui ui minus 1 plus ui by 2 whole cube. Okay. So then mean power for a given wind speed distribution is summation over all I half rho of air phi ui ui minus 1 plus ui by 2 whole cube by phi ui. Okay. So here basically if you compare it from with the mean distribution of velocity u cube, it's phi ui into the mean velocity for that interval, summation of that by summation phi ui. Here you have this entire thing into half rho just multiplied with this and this summation phi ui. Okay, so basically this is equals to half rho u cube, correct, the mean of u cube. Remember that since phi ui is ni by delta ui by n, so summation phi ui is equals to 1 by n summation ni by delta ui. Okay. So for the specific case, when you have delta u are all equal to each other, that is delta u1 equal to delta u2 equal to delta u3, this delta u can be taken out and these two cancels and you get 1 by delta u. Okay, so this term just becomes into delta u. Okay, that's what it becomes. All right, so this kind of gives you an idea of how from anemometer readings of velocities you can evaluate the mean power and mean wind speed distributions. Okay, so let's look at this idea a little bit further. So this kind of gives you the raw distributions. Okay, can we fit these distributions into some established probability PDF functions? That's the next question, because if we can fit this existing the wind speed distributions into existing PDF distributions, then the task of finding means, averages, medians, standard deviations, etc. becomes significantly more easier. And the answer is we can do that under most circumstances. And the distributions that are usually being used is what is called the Weibull distribution, and we will see what those distributions look like.